Okay. Good afternoon, everyone. So I am Dr. S.S. Rathod from Sardar Patel Institute of Technology, Mumbai. My today's talk is on how to improve the experiences of students in the laboratory in an engineering education. A laboratory is a very important component in engineering education. Laboratories foster a range of skills, including communication, knowledge, teamwork, ethics, and it encourages information acquisition. Laboratory classes are integral part of any engineering education course. I propose, as far as possible, all the courses must be supported with the laboratories. Students cannot learn how to test circuits without going to a laboratory, just as human beings cannot learn how to swim without diving into the water. However, conventional engineering laboratory strategies are not sufficient to meet today's course outcomes. It is very challenging to design laboratory courses which will motivate students to spend more time in the laboratories. In traditional laboratory-based experimentation, students follow a predetermined procedure. This allows students to manipulate the equipment, learn standard techniques like collection of the data, interpretation of the data, and writing a report. However, the level of critical thinking required to perform an experiment and consequently the deep learning achieved is not significant. Furthermore, cooperative learning between the instructor and student is not facilitated in the traditional lab methods. A more ideal approach is required that integrates application of knowledge to solve the problems, to enhance the group work, and an opportunity to design an experiment, including consideration of safety aspects. Student satisfaction level must be at the core of the improvement in the laboratory experience that must be recorded and analyzed for corrective actions. Increasing the level of student satisfaction can benefit student learning. It has to be recognized that for students to obtain the necessary laboratory skills to use the lab facilities effectively requires a significant commitment of time for both the instructor and the student. The primary goal of improvement in the laboratory experiences are enhancing understanding of the course matter, developing teamwork abilities, developing practical skills, developing scientific reasoning, understanding the complexity and ambiguity of the empirical work, and cultivating the interest in learning. Primarily, it is an improvement with regard to conducting an experiment, recording observations, and analyzing an experimental data. Okay. So now I will talk about our basic laboratory learning model that we have adopted. So primarily, human resources are very important whenever we talk about the laboratory. Exceeding the student's expectation does not happen by mistake. It must be deliberately managed by someone in the program. There have been a number of studies looking at the laboratory management and how it can be used to manage the quality, safety, and resources in the laboratories effectively. For example, this is one of the learning model shown in figure 1. It has been published in one of the IEEE transactions paper published in 2015. What it tells you is that it is hard to manage and ensure quality with so many laboratory-based courses. Thus, it requires a proper laboratory management. There are several course coordinators, laboratory in charges, and various laboratories distributed in the various departments and sometimes interdepartment for interdisciplinary courses. So the effective coordination between various laboratory in charges is required, which can be fulfilled by having a laboratory manager at the department level who can be made accountable. To manage the conflicting needs of software, sometimes open source is required, sometimes proprietary software is required, then choice of the equipments, etc. So a laboratory management is a manager who can decide what is to be there in a particular laboratory. The laboratory manager would work in close with the course coordinators and technical staff to coordinate any improvements to each laboratory identified via an instructor or student feedbacks. It is necessary that laboratory manager must work closely with lab in charges and all the course coordinators. Now this figure shows the process for improvement the laboratory experiences of the students. This process we have already adopted in our department. There are various novel methodologies that goes as an input to the process. Like for example, we can have pre-lab video demonstrations before the actual experimentation that student carries out in a laboratory. We can have uses of online labs or the resources. We can decide when to conduct the simulation experiment and when to conduct the actual physical experimentation. Then there are various graphing resources that nowadays students need to be provided. Then there are quick guides for the post-lab stages. There are lab evaluation guidelines. Then there are citations and the references so that student can draw proper conclusion at the end of the experimentation. Then sample lab report to be provided to the students. Then student will be able to design his own experiment and a free lab toolkit, about which I will discuss in after some time. So these are various novel methods which goes as an input to the laboratory enhancement process. We need to identify students' requirements and their abilities to perform an experiment. Otherwise, how do we enhance a performance of a student without knowing the student's abilities? For example, differently able students can be instructed in a different manner as compared to a normal student. A student who is having a hearing problem has to be instructed in a different manner. So we need to ensure that all students, including students with disabilities, have equal access to educational opportunities. Services for students with disabilities should be implemented in laboratories, like for example, extended time, which we already give to the students during the theory examinations. So similarly, we need to provide an extended time for the students during the experimentation. The use of assistive learning devices. So you cannot have the same mechanism of content delivery to a normal student and a hearingly impaired student. So it requires a different assistive listening device. Then alternative media, peer advisors, then disability related equipments, and particularly handbook for students with the disabilities. So if student comes with a disability, then all these things should be provided so that a disabled student feels to come to a laboratory and perform an experimentation. Then safety guidelines and emergency evacuation procedures need to be given to all the students and particularly to the disabled students. Feedback collection is a driving factor for any improvement. Thus, in this process, it has been shown that we collect the feedback from various stakeholders like students, then faculty, technical staff, and other experts like examiners who come during the examination at the end of the semester. We collect this feedback and the necessary corrective actions are being taken care. So now next point is how to manage and improve the design of the laboratory. Design of laboratory and an appropriate experimentation requires significant quality time. However, it is at the core of the improvement in the experimentation. Design of an experiment plays a major role in student level satisfaction. Thus, first we need to find out whether you want a simulation laboratory or the physical experimentation. There are numerous uses of simulations in the laboratory. Simulations can be used as a pre-lab experience to give students some idea of what they will encounter in an actual experiment. This can improve laboratory safety by familiarizing students with the equipment before actually using it. It also can result in significant financial savings by reducing the time a student or team needs on real and expensive laboratory equipment, thereby reducing the number of laboratory stations required. Simulations can be used as a standalone substitutes for physical laboratory exercises. Simulations are also useful for experimental studies of systems that are too large, too expensive, or too dangerous for physical measurements by undergraduate students. For example, TCAD, that is Technology for Computer Aided Design. These are the tools that are used in a second year electronics engineering course called Electronic Devices. We have introduced TCAD into the second year course called as ED, that is Electronic Devices, and it has been observed that it gives more understanding of the concepts like band diagrams and electric fields, which cannot be observed physically by an experimentation. The use of TCAD tools allows students to learn the fundamentals of device processing in a virtual environment and help them to acquire critical thinking skills while having an authentic design experience. Proficiency with the use of TCAD tools has become a necessity in modern manufacturing environments, particularly in semiconductor industry. Introducing TCAD tools also better prepares students for semiconductor device research in advanced courses. Then the next measure can be taken is the students themselves solving the challenging problems by designing their own experiments. So instead of following an established procedure given in the laboratory manual, student will be given a scientific problem and will be able to design his or her own way of solving the problem. The problem statement should be put up in such a way that it gives challenges to the students. The students' involvement in the laboratory increases if the experiments are designed and executed by students themselves. Then the next point is mini projects. So project-based learning, that is PBL, motivates students to learn actively. So it can be widely applied to many engineering courses. Mini projects provide opportunities for the students to develop project management skills while learning in a team. So the group work is important to prepare students for employment and to overcome socio-economic barriers. Thus, there need to be some laboratories which are devoted for the mini projects. Then optional experiments. Students are required to select one of the 3 optional experiments relating to their field of interest upon successful completion of the mandatory experiments. This I am talking in particular with respect to our institution, which is affiliated to Mumbai University. Thus, from university we get a list of experiments which we call it as a mandatory experiments, which each and every student needs to be performed. And based on those mandatory experiments, we give the gradation to the students, that is marks to the students. Thus, we want that teachers should give more experiment, more over and above the mandatory experiments to the students. They are called as optional experiments. Thus, experiments designed for a particular course should be more than the minimum required experiments. Then course-based independent development of the laboratories. For example, there is a course on wireless communication or there is a course on analog circuits. Then they require the special care or the laboratory need to be designed as per the contents of the curriculum. So we can have course-based laboratories. Now next point is how to manage and improve the resources in the laboratories. So the first resource is a teaching assistant. Demonstrating in a laboratory is very different from teaching in a lecture or tutorial, as a wider range of skills are needed. Demonstrators need to know how to teach, how to manage students, how to use instruments, how to monitor the lab safety, and most importantly, how to troubleshoot electronics related courses. Now many of the demonstrators had strong theoretical knowledge but were severely lacking in terms of practical skills. This problem needed to be rectified because the laboratory is important for development of hands-on skills, and it was unacceptable to have demonstrators lacking these fundamental skills. So the regular training programs should be organized on how to use the equipment in the laboratory, as well as an understanding of how correctly to troubleshoot the problem. We recommend these courses to be organized for all the teaching assistants, and we organized one course per semester for the teaching assistants. The next is a free toolkit to each student. We believe in a philosophy called as one student, one experiment. So for conducting experiments of various subjects in electronics engineering, students regularly need some of the components. For example, students require a breadboard, soldering gun, multimeter, connecting wires, etc. To effectively implement our theory of one student performing one experiment at a time and not in a group, in some of the courses where component-based implementation is possible, and every student can perform an experiment independently, we have proposed a scheme and it has been implemented in 2013-2014, through which we have donated one free kit containing these parts, that is breadboard, soldering gun, multimeter, connecting wires, etc., plier, etc., to the students. And it was a free toolkit. We have observed various benefits of giving these free toolkits to the students who enter into the second year. The benefits are, like, students need not issue every time they come to the lab all these components, and it saves their time. Students mount these components in their free time and they can even test circuits at home. During their entire undergraduate study, they carry the same kit and perform the experiments. So they are familiar with the entire toolkit. They regularly use that multimeter and soldering iron. It has actually enhanced their capabilities in using these components. If experiments remains incomplete in the allotted time, they can continue in the next session and need not mount the circuit again, which used to happen earlier. For example, if there is a big circuit, then student gets a 2 hours of a time and student does not finish that within the 2 hours. So he dismantles the circuit, and when he comes for the next laboratory session in the next week, then again he has to remount the circuit. He has to start from the scratch. So through this toolkit now, he saves his time because the circuit remains with him. Student also troubleshoot this circuit in his free time or at home. So now teacher can give big circuits for the testing. This toolkit is helpful for the students for execution of the final year projects and the mini projects. We have also observed that students have become more disciplined after giving these toolkits to the students. And as an administrator, one of the important points for us of giving this toolkit is that it saves the time of the technical assistants. The next measure that can be taken in the laboratories is use of Moodle, that is Modular Object-Oriented Dynamic Learning Environment. Moodle is one of the popular open source tools used to manage learning resources. Nowadays, educators' job is changed from being the source of knowledge to being an influencer and connecting with students in a personal way that addresses their own learning needs. A healthy amount of connected behavior within a learning community is a very powerful stimulant of learning, not only bringing the people closer, but promoting the deeper reflection and re-examination of the existing beliefs. This can be implemented in laboratory experiments via Moodle. The college students believed that Moodle is a very effective tool through gathering of knowledge via uploaded the handouts and upholding discipline via time management. Then the next measure I recommend is the use of mobile phones in the laboratories. Through the mobile technology, we can better engage students and help improve their performance in laboratories. Mobile technology is impacting nearly every aspect of our lives, and the way we learn and teach is no exception. These technologies can level the playing field in the laboratories for each and every children. So the children may be from different family backgrounds, for example, different economic backgrounds. This is also true for the students who come from low-income households. Many families do not own a computer, but nowadays they do have mobile phones. It is no longer adequate to teach students the way we were taught. First, let the students use mobile devices in the laboratory sessions because they are already using them in their day-to-day life. We need to provide kids with the opportunities to work through real-life problems, real-world problems, using the mobile technology they know so well. For example, learning about sound waves and wave frequencies by reading about them in a textbook, or simulating a circuit using an online oscilloscope program. Which one of these two students will take? I know which one my students will choose. So students today, regardless of socio-economic background, are 21st century learners. Mobile technology is a way to capture and sustain their interest in laboratories so that they become the innovators. All students will enjoy the use of apps for instructions and feedbacks on their smartphones rather than teacher teaching them in the laboratory sessions. So the student shift from being dependent to being an independent information seekers is necessary. This figure shown or the snapshot shown on the screen shows that one of the app I have used in a VLSI design course for simulating a circuit called as CMOS inverter. A primary disconnect is the fact that many teachers just do not know how to use the mobile devices as an education tool. Teachers must embrace mobile technology just as our children and every major business sector and industry have. Now next is using online resources like nanohub.org. Nowadays, substantial amount of resources is currently available on the internet that is free and useful in teaching skills used in the laboratory. Nanohub.org provides computational resources available as online research and education platform. Computational resources available on the nanohub.org have been incorporated as a part of laboratory session in a course called as IC Technology, which I teach in semester 7 in Electronics Engineering Department. Experiments are carried out during the course that allow students to enhance their understanding of theoretical concepts dealing with the nanoelectronics materials and devices, and it has motivated students to use the online compilers. One of the most successful examples of using e-learning methodologies, I would say, is that nanohub.org. From pedagogical perspective, and even though nanohub.org is very well organized, it is very well managed, and it is important to guide students in order to help them browsing through the enormous amount of multimedia data they can access. Then the next method or the improvement method that can be adopted in the laboratories is the virtual remote laboratories. Virtual and remote laboratories are e-learning resources that enhance the accessibility of experimental setups, providing a distance teaching framework which meets the students' hands-on learning needs. In addition, online collaborative communication presents a practical and constructive method to transmit the knowledge and experience from the teacher to students, overcoming a physical distance. So students must carry out their practical activities in an autonomous way. Therefore, if teachers want to facilitate their work, he should be able to do it through virtual labs. Nowadays, people are designing laboratories based on the tools like, for example, LabVIEW based remote triggered virtual laboratory. That means students can not only simulate the virtual outcomes of the experiment, but also control the real instruments while they are located elsewhere. Then the next enhancement can be pre-lab video demonstrations. Laboratory experiments are usually created with the understanding that students have already obtained a satisfactory level of prerequisite knowledge in the use of various hardware and software, which is a pre-assumption because it's not true in many cases. Thus, it can cause significant stumbling blocks for students without these skills. The use of multimedia and online technologies can help bridge the gap with deficiencies in required knowledge. It helps the students to think about the lab scientifically before they actually perform the lab. There is increasing evidence that pre-lab sessions are beneficial to the students' learning. It increases students' confidence to carry out the activities during the lab sessions. In particular, developing video resources can be time-consuming, but it is definitely beneficial for the student learning. Videos may contain the information regarding history or background of the equipment, application or use in an industry, description of the various parts used during the experimentation, operating principles, variations of the instruments, capabilities and limitations, advantages and disadvantages, possible errors in using the equipments, maintenance and care about the equipments, safety precautions, and equipment demonstrations, along with the course content. The next point is the networking in a laboratory. Network environment can give access to an immediate data. An instructor is able to make available resources immediately to all the students. Thus, it is very important to have a networking in a laboratory. All computers needs to be networked, and there has to be a centralized supervision for that. Then the next point is help provided to the students during for writing the laboratory report. Thus, helpful hints can be provided to the students on how to prepare, how to improve each component of the lab report. For example, how to improve the title of the experiment, how to improve the presentation on the report. For example, what is the correct format for the tables? What is the correct format for the figure? What is the correct scientific writing style? Then what should be the problem statement, correct problem statement, how to have a proper logical reasoning. Then for example, results. Results must begin with effective statement of oral findings, and results must be presented visually, clearly and accurately. Conclusion section must convincingly describe what has been learned in the laboratory, whether expected outcomes are met or not met. It should provide sound judgment based on the evidences. Clear evidence to judgment must be provided in the findings, and how evidence contributed towards judgment must be able to show. Primarily, student is able to establish the science behind the experiment. That is, laboratory procedure is expected to yield certain results, and to a certain extent, the quality of the experiment depends on whether or not those results are obtained. Report must list all the appropriate sources of the references. So students should be provided with this kind of a help. Then the other resources that we can provide for improving the laboratory experience of a student are graphing resources. Nowadays there are a lot of tools available with the help of which student can plot various types of graphs and they can come up to a proper conclusion. So we can provide different graphing resources. Then lab guide, a guide to a student which will tell how to collect, how to manage and how to analyze the data. Then quick guide to the post-lab stages, like for example an abbreviated version of the post-lab stages to be used as a quick reference. Then lab checklist, then lab evaluation guides, then online writing handbook which will help students about the grammar, style, punctuation, mechanics and the search engines. Then citations and references, advice related to citations and expenses. Then sample lab reports. A good lab report can be provided as a sample. Assessment of any course is very important. We for laboratory courses we do assessment using 3 strategies. Number 1 is we have implemented rubrics for the assessment. Second is peer evaluation, and third is the industry feedback. So first I'll talk about industry feedback. The goal of the industry survey is to find out the relevance of the contents of the lab course to an industry. So whenever an industry person visits to the department, or we call sometimes industry person to the department, and we show the different kinds of laboratory setups that are available with us. For example, in last semester, Siemens people have come to our laboratories and they have given us some suggestions about the laboratory equipments or laboratory experiments that are carried out in instrumentation laboratory. So their feedback is very valuable. We consider that feedback and we do the innovations or the improvements in the laboratory experiments. We upgrade the equipments, etc. Then the peer evaluation, which we have implemented in some of the courses. In peer evaluation, student is supposed to evaluate an experiment done by another student. A student did not have to evaluate himself. Each team member evaluates the other fellow team member on the contributions of different problems. For example, what is his contribution above the team norms, or as per the team norms, or below the team norms, and then comment on the results obtained by the other students for the same experiments. If there is a deviation, why that deviation is there. So that we call it as a peer evaluation. And the next is the assessment with the rubrics. A redesigned assessment strategy was implemented to target the problem areas of scientific observation and report writing. We have prepared various rubrics for the laboratory assessment. There are 10 performance indices. So this table shows 5 performance indices and in detail all the rubrics. And this next slide shows rest of the 5 performance indices and in detail the rubrics that are prepared. Now, for example, first rubric is, or first performance index is preparedness. That means we expect that students should come prepared for an experiment to be performed. We grade every performance index on a scale of 1 to 5. Students get 5 out of 5 if student is aware about the experiment to be performed. He knows the basic theory, he knows the circuit diagram, he knows that whether the components are available in the laboratory, he never forget to bring the assisting materials like calculators, semi-log paper, graph paper, and he also sees information from multiple sources. That means he has done everything required to perform an experiment. So we give 5 out of 5. Now I would give 1 out of 5 if student is not aware of the experiment to be performed. He is unable to perform an experiment independently. He does not seek information from the other resources. Primarily, he is not aware of the experiment to be performed at all. Then our second performance index is tool selection. So whether student is able to select the tool on his own or not. Based on that, we grade a student on a scale of 1 to 5. The next is tool operation. Whether the student is able to operate that tool on his own or not. Next is experimental procedure. If there is a standard experimental procedure, whether he follows the standard experimental procedure properly or not. Then debugging capacity. How student traces a circuit, how he measures the voltage at each stage. Based on that, we rate a student. The next performance index is effort. If student does not get the output, whether he is ready to wait for some time in the laboratory and spare more time to get the results. For example, in lunch break or after his college hours. So based on that, we rate a student. Then result and measurement error. If student doesn't get the results properly, then whether he is aware of the measurement error, and if he is aware, then whether he is able to account for it statistically. The next performance index is analysis and theory application. Whether he is able to analyze the data that he get and whether he is able to interpret it carefully and apply it to the theory that he has learned. The next performance index is documentation. So whether he is able to properly write the lab report. That is what is this. That is, a student writes experiment number properly, he writes the date, he writes the objectives, apparatus with the specifications, software use, etc. And finally, but most important, is lab ethics. That is performance index 10. His punctuality, his proper use of the equipments, whether he follows the safety procedures, cleanup procedures or not. So all these are performance indices, and we have implemented these performance indices in the laboratories. Now I would present some of the key findings or results of whatever novel methods we have adopted. So for some of the things I will present, for example, nanohub.org, use of nanohub.org, which I have extensively used in the 7th semester IC technology course. There are various experiments that are performed in this course. For example, simulation of an oxidation process with Deal-Grew model was the one of the experiment. Then simulation of diffusion process for different conditions was other experiment. Then simulation of PN junction for various structural and environmental conditions. Then simulation of MOS capacitor for single gate device. Then simulation of MOS capacitor for quantum simulation. Then simulation of bulk silicon SOI technology MOSFET and then the double gate MOSFET. Then carbon nanotube field device simulation. Then CNT FET simulation for varying conditions. Then silicon nanowire simulation. Then comparison of SOI and double gate MOSFETs. So I have used multiple tools available on the NanoHub. For example, there is a tool called as FET Toy. There is a tool called as CNT Mobility. There is a tool called a TCAD Lab or MOSCAP Lab. So all these tools I have used, and I have performed various experiments, or students have performed various experiments, and then I have taken feedback from the students, and these are the results that I am presenting before you. For each experiment, student reported the resources available in the nanohub.org, such as presentations, course notes, CAD simulation tools, animations, learning modules, bibliographical references, links to pages, etc. Students attending these experiments were surveyed in order to give us their feedback to improve the quality of the course in terms of content, learning resources, and pedagogical procedures. As shown in this figure 4, majority of the students are interested, motivated, and satisfied with the use of NanoHub. While figure 5 shows that majority of the students strongly agree that their laboratory experience is improved with the use of NanoHub. These are the results or our experiences of assessing with the rubrics. First time we have implemented these rubrics, which I have shown in the table, in 2012-13, and then we carried out the same in 2013-14, 2014-15, and this year also we are assessing the laboratories with the same rubrics in 2015-16. Feedback from students and the staff indicate that rubric is an effective resource and that has enhanced involvement of students and learning in the laboratory. It is found that in 2012-13, that is this first column, when performance indicators were implemented first time in the laboratory as an assessment tool, students did not take it seriously and hence their attainment was very less. Since it is an affiliated institute, students thought that we will not actually implement this performance indices and we are simply telling them, but we actually did the gradation based on the performance indices. So however, when the students realized that these performance indices are affecting their grades, they took it seriously from the next year. So there is a significant improvement in 2013-14. So now significant improvement in the laboratory sessions can be observed, particularly with respect to some of the performance indices. For example, PO4, PI4. However, performance index 1, that is PI1, I call it as a preparedness for the laboratory session, is somehow still it is low. We have also collected feedback from the faculty who are using as well as who are not using this performance indices is taken. It has been observed that some of the faculty members are reluctant to introduce this into their courses. This can be attributed to the time required for the assessment of all the students is significant. However, those who have adopted these rubrics, they are satisfied and the level of improvement is observed into the students. So to reduce the time required for the assessment, what we did is we have prepared an index sheet on which we have graded the 3 experiments cumulatively for these performance indices. We call it as a midterm feedback, and we give that feedback to the students in writing. That is, students are graded on all these 10 performance indices in the midterm. So teacher has to do it only once in the midterm. Then teacher will again do it at the end of the semester, and again student is observed for the improvement on these performance indices. Thus, now the teacher's burden is slightly reduced. He has to do the assessment only twice, in midterm and the end sem assessment. So this is the feedback from the teachers. It shows that teachers strongly agree that yes, there is an improvement in the laboratory experience of the students. So finally, these are my recommendations from the experience that we have gained in the last 3-4 years of these novel methodologies, particularly giving the free toolkit, use of the recent technologies like Moodles, mobiles, and use of NanoHub. nanohub.org, use of novel assessment methods like rubrics, etc. So my recommendations are train and manage the lab resources properly. Then conduct the interesting pre-practical activities, for example, videos based on the experiments. Then provide online as well as offline learning materials. Then encourage the preparedness for the practical sessions, and still we are struggling with this part. Then harness the technology to engage the students, for example, Moodle, NanoHub, or mobile platforms. Then encourage the culture of feedback and devise the innovative feedback mechanisms. Then devise the novel assessment techniques, for example, peer-to-peer feedback. Then focus on the skills resulting in increased employability. Then encourage the independent research-based projects, that is PBL-based learning. Then give the challenging problems to the students to design the experiments so that they become more interested. And finally, last but not the least important, take care of the differently abled students so that they come to laboratory and spend more time in the laboratory sessions. These are the references. Yes, references. Thank you. Thank you very much. Any questions, please?
We will give the attendees 1 or 2 minutes, sir, so that they can enter their questions.
Yeah. Okay.
In virtual laboratory, we perform the experiment by simulating the codes or circuits. Is it really helpful for the student to improve the laboratory and learn more about the experiments?
Hello?
Yes, sir.
Yeah, sir. Virtual laboratory we have performed only on FPGA, platform. In FPGA, our FPGA is reconfigured in such a way that student can sit anywhere and then he can write a VHDL and Verilog code and then he can download. So only that kind of link we have established. So we have found that if I give a student homework on let us say VHDL or Verilog, I tell them to write a code and test it and come up with the synthesis report, then he can actually do it from anywhere, and that was very good. So at least one of the course I have tested and few experiments we have tested, and we found in that course it was very good. But others we have to test. We are developing one of the laboratory which is LabVIEW based laboratory, but still I don't see that much improvement we will really get out of it. But in FPGA and microcontroller based courses, it is definitely helpful.
Have you used the virtual lab vlab.co.in, the MHRD NMEICT initiative?
No, sir. No, sir. No. That I have not used. Actually, I had tried once to log in, but that I could not. Somehow I could not establish the link. I have tried 2, 3. Some IITs are also I won't name, but some IITs are providing the virtual labs, and they want the login. So I tried to log in there, but I'm not. Sometimes I'm not getting the feedback on the either password they are not giving. If it is given, if I had been issued the password, then I am not successful in implementing the lab. That is true.
Can you explain a little more about mini project laboratory improvement?
Yeah, sir. So what we did here is that we have allocated one room, and we call that room as the workshop, actually electronic workshop. And in that room, what we did is it's a physical resource. So we have kept some of the equipments like CRO, multimeter, power supply, and some other resources, and they are available 24 hours to the students. And what we did is that earlier mini project laboratory reports or whatever reports we have done or the projects, they are available in those laboratories. So it is 24/7 open facility to all the students where they can sit and they can execute any mini projects. So if any teacher in any course uses a student to perform a particular hardware related experiment, then he can go to that laboratory, he can sit over there and he can perform an experiment. So that is what we did. Means all resources are available at his doorstep, they are available over there.
How do you define the skills resulting in increased employability?
So, I mean, like for example, student, he's an electronic student, let us say, and he doesn't know how to troubleshoot a circuit. It is not good. For example, if I tell our students, today only I was discussing with the students, second year students, and if I give them the component and I tell them what is this, so they will immediately look at it and say that it is a transistor. So why it is a transistor? Because it has three terminals. So that is not correct. Any device which has a three terminal, is it mean that it is a transistor? No, they need to characterize the device. So what is an industry perspective is that, according to my knowledge, is that students should know all the details of all these components. So now in laboratory, what we expect is that whatever is the component, whether resistor, capacitor, or any other integrated circuit, we provide the data sheets to the students. And what we expect is that when they go in an industry, they should not go only with the theoretical background. They should know how to implement it, how to use that component, what are the specifications required. So that is what is my understanding over here.
Do you have a Moodle setup? Moodle is resource intensive.
Moodle, sir.
Yes, sir.
Now, what are you asking? Moodle? Yeah. We use Moodle regularly. In entire campus, we use Moodle.
I think they are
It's not only
concerned about the how to set it up.
hello?
Yes,
Sir, I could not hear you. Your words are.
They said, is that Moodle set up for you?
Yeah. In our college, we have an MCA department, Master of Computer Applications. They have actually set up the Moodle for us. So we have an administrator in MCA department, and if I require anything, then I contact that administrator, and he gives the rights and everything, and then I can manage my course, entire course on the Moodle. I can upload my PPTs, I can conduct quiz. That we do regularly.
Have you tried any open-ended experimentation in VLSI lab? Can you please share a case of what students did there?
No, open-ended experiments means like online compilers, like this one org, nanohub.org or something else. Open-ended means, sir?
I think they can clarify. We will take the next question when they reply. I am dealing with DSP lab using MATLAB. What kind of Moodle resources can I use?
Model resources, sir, DSP, I'm not a teacher of DSP, but then our Professor KD Talele is there. He uses it extensively. Sir, on Moodle, these resources are not course centric. Moodle is used to share the information. Through Moodle, you can actually upload your course contents, you can conduct a quiz, you can give the assignments, students can upload their answers through the Moodle, you can set the deadlines for the submissions. Then you can actually do the chatting through the Moodle. That means student can ask you the question at any point of time. Then you can give the answers. Then you can have a collective feedback analysis. All those things you can do. It is not a course centric. You can do it for any course.
For VLSI design, so many tools are available. Among them, which one is effective and worth?
Sir, it depends on a course. Like for example, I teach a number of courses in VLSI. Like for example, IC technology, integrated circuit technology. It's a VLSI technology course. Now in technology, what we do is, earlier we used to have a TCAD tool from Cogenda. Cogenda is a company, like Synopsys gives you Centaurus TCAD. Like we have a Cogenda tool set. But that is a license tool set, and there are some limitations. Like for example, if I have 5 user license, only 5 students can perform at a time. And but then nanohub.org is a free resource, online resource available, and students can perform it at any point of time. So what I did is I conduct most of the experiments in that course on nanohub.org, and then 2 or 3 experiments on a commercial tool like TCAD. Then we have another course called as Basic VLSI Design, in which they study the CMOS inverters, NAND, NOR, SRAM, DRAM, clocking, etc. Wherein they need to know the SPICE coding, because it's a circuit simulation. So what we do is we use LT SPICE for that. LT Spice. It's an evaluation version you can download, and that is enough for us in an education institute. So we conduct our all the experiments on LT Spice. Students, they write a Spice code and they simulate all these circuits. Then we also have one more course called as ED, electronic devices, wherein students study the band diagram, energy band diagram, like PN junction, heterojunctions, then the JFET or your MOSFET, details of this, internal details of this, including threshold voltage or interface traps, etc. So to study all these concepts, they require basically a TCAD tool. So there also we have implemented TCAD tool. And then the next course is called as analog VLSI design. In analog VLSI design, it is offered in the 8th semester, which is currently going on. Again, in analog design, basically they require a SPICE tool set. So we implement it using LT Spice, any SPICE tool set. Actually, I give option to the students. One is the LT Spice, another free tools. We always use free tools. Like another one is the M Spice, or third one is an electric, which any one of these they can use. So I don't make students tool dependent. Any tool they should use, but finally, whatever my objective or problem statement is there, they have to simulate it.
How can industry
We don't sir, we don't have commercial like Cadence or Synopsys is not available with us. We do have Mentor Graphics. We do have Mentor Graphics. Entire HEP1, HEP2 module is available from Mentor Graphics. But then Mentor Graphics, if I ask students to perform the experiments using Mentor Graphics, then what happens is 2 hours are not enough for them. That is what is my observation. I introduced Mentor Graphics in 2011, 2012. Then I found that they are not able to finish experiment in 2 hours. Forget about 2 hours. Even in the next lab session also they cannot complete, because it's a commercial tool and they have to follow each and every step, and it is server integrated. So the server is having a license or client machines. So a lot of technical problems. Finally, what I did is that I asked them to perform only one experiment on a commercial tool, 1 or 2 experiments at the most. That's it, through which they can understand all the steps. Yes, sir.
How can industry feedback be implemented for digital signal processing?
Sir, DSP, actually DSP I can't comment, because DSP course I don't even teach. So, but in industry feedback, in DSP we have not taken actually. We have taken in instrumentation related courses. We have also taken in some of VLSI related courses like FPGA, CPLD based those courses we have taken. But DSP we have not taken actually the feedback. So I don't think I will be able to comment on that about DSP courses, because professors are different, and we have a professor who is teaching DSP from last 22 years here in the same college.
The previous person who had told about open-ended experimentation involves students to design then own experimentation and analyze the responses.
Yes, sir. Exactly. This is very well possible in instrumentation laboratory. That is what we observed. We only tell them, like for a simple case, like for example, I would like to implement the temperature measurement. These are the limitations. You will use these components, you will use, let us say, LabVIEW, you will use something, and then design an experiment which will effectively measure the temperature. Then they should come up with entire experimentation setup, kind of a mini project you can say, and they should suggest that, sir, this will be our circuitry, this is how we are going to measure the temperature. Then students are obviously interested if they want to, and they have to prove it that yes, their circuit is correct. So that is called as an open problem, open statement.
As you said, how the
but then in one course, hardly one or two open kind of things are possible in the laboratories, because students will come up with a lot of multiple choices. For example, somebody requires 1K resistor, somebody requires some 4.7 and different values of resistors. So then you should have that many things available in the laboratory. So it's a challenging, but then yes, it is possible.
As you said, how the toolkit can be provided to microprocessors labs.
What, sir? What?
How the toolkit can be provided to the labs.
Sir, what we did is, what I did is in 2012, I have implemented that as a scheme. it was my observation that number one is our technical assistant used to spend a lot of time in issuing the components like multimeter, soldering iron, etc. Student used to come to the lab and then she used to issue the components. If there is a 2-hour experimentation, half an hour she used to do that. Second point is that students every time get the different kind of a multimeter or different setup, sometimes portable, sometimes AC based. So every time they have to struggle with those equipments rather than the actual experiment. Then the next point is we also observe that students are not so disciplined. For example, at the end of the semester, if you open your power supply, you will find that inside that power supply there are multiple connecting wires. There are a number of connecting wires just for the sake of putting students put inside it. So now how to improve entire situation? So what I did is I have requested management to fund some money so that we can give one free toolkit to every student. So what we have given is one microcontroller, one multimeter, one breadboard, one soldering iron, some connecting wires, uh, this kind of things we have given in a box. And we tell them that now this is your box, you take it, you keep it with you for entire engineering education. We will not issue multimeter or soldering gun henceforth or any component. So now what student does is he only for performing any experiment he requires few components like microcontroller or some ICs, correct? So that he has to issue regularly from the laboratory. So we call this as a free toolkit and we have really observed the benefits of this. Students have become disciplined, very well disciplined, because now you don't find connecting wires here and there, because if one wire is not found in his kit, then he will struggle, where is my wire? So it's good. And multimeter also they use very judiciously, and since it is available 24 hours with them, now we can tell them now you simply use it, take these components at your home, perform an experiment and then come back. So it is very good. This strategy is very good.
Is it applicable to electrical students also?
That is, I think, but then in electrical, if electronics related courses are there, sir. In electrical also, we have electrical department in SPC. So they have some electronics related courses and now many courses actually. There it is, there they can use. Like operation, linear integrated circuits is nowadays, it's a course in many electrical engineering department also. There you can use it. Wherever component related courses are there, you can use it. Or PCB kind of students are working on a PCB where they require a soldering gun or some breadboard kind of a testing. There they can use it.
Thank you very much, sir. I will send you the recording.
Thank you, sir. Yeah, sir.
Thank you, sir.
Sir, is done or any other
Yes, sir.
question?
All the questions. Those are all the questions, sir.
Okay, sir. Thank you. Thank you very much.
Thank you, sir.
Okay.